Hey guys, today we're going to look at the relationship between continuity and differentiability. In this particular lesson, we're going to check when a function is continuous, does that mean that it is also differentiable? As well as if a function is differentiable, does that mean that it must be continuous? Now, differentiability is simply the fact that a function is able to be derived, meaning I would be able to find the derivative of a particular function at a particular x value. For something to be undifferentiable means that if I were to find the derivative and plug in that x value, I would get something that is undefined. So let's consider this particular graph. We have here f of x is equal to the square root of x squared minus 4. Now, based on this graph of f of x, is it continuous at x is equal to 2? And then we're going to explain. Whenever you're asked about continuity, you have to remember the three-part definition of continuity. And we use that in order to explain our answer. So as a reminder, the three parts of continuity consist of 1, that the function is defined at a particular x value, 2, the limit exists at that particular x value, and 3, that the function value and the limit value are the same. And that's how we would explain if a function is continuous. So for this particular function, we would first have to find the defined value, so f of 2. And when I look at my graph, f of 2 is equal to 0. Now we would go ahead and establish the limit. So the limit as x is approaching 2 of f of x. If I look here, remember that the limit, in order for it to exist, the left side must equal to the right side. Now the right side is approaching 0, but we see that on the left side there's nothing there. Therefore, the limit does not exist. And because the limit does not exist, this means that f of x is not continuous at x is equal to 2, and we would say because the limit as x is approaching 2 of f of x does not exist. Now we're going to see if we can find the value of f prime of 2 in order to determine if f of x is differentiable at x is equal to 2. So I'm going to go ahead and take my function here. I'm going to rewrite it as x squared minus 4 raised to the 1/2. And I'm going to go ahead and find that derivative. So f prime of x would equal to 1/2 times x squared minus 4 raised to the negative 1/2. And because of the chain rule, I have to multiply by the derivative of the inside, which is 2x. Here the 1/2 and the 2 would cancel. And because this is a negative exponent, that means that the square root of x squared minus 4 would have to move down to the denominator. So my f prime of x is equal to x, that stays in the numerator, over the square root of x squared minus 4. Now we're ready to plug in 2. So f prime of 2 is equal to 2 over the square root of 2 squared, which is 4, minus 4. Now here we end up with 0 in the denominator. So what this means is that this derivative value is undefined. So that means that f of x is not differentiable at x is equal to 2. Now, in case this was a calculator question, I want you to see what would happen if you were to try to find the derivative of a function that is undifferentiable. So we're going to go ahead and graph this function. So I'm going to open my parentheses, x squared minus 4 raised to the 1/2. And now we're going to graph. And even though I have it here, I just want you to see what the calculator would do. So I'm going to go to second calc to try to find my derivative. I'm going to click on dy dx, and I'm going to press x is equal to 2 and enter. And we get here an error, non-real answer. This means that it is undifferentiable if you get that error. Let's move along to look at some other graphs in order to see if we can establish the link between continuity and differentiability. Here we have the graph of f of x, which is equal to x raised to the 2/3 plus 2. Based on the graph, is f of x continuous at x is equal to 0, and we would explain. So first I would state that f of 0 is equal to 2, since here is x is equal to 0. The limit as x is approaching 0 of f of x is also equal to 2. Therefore, because the function value is equal to the limit value, we would state that f of x is continuous at x is equal to 0 because f of 0 is equal to the limit as x is approaching 0 of f of x, which is equal to 2. Now we're going to see if we can find f prime of 0. So I'm going to take my function here. I'm just going to find my derivative. So f prime of x is equal, this is just a power rule function. So I would bring the exponent to the front. So 2/3 x, and then I would subtract 1, which is subtracting 3 over 3, and I get negative 1 over 3. So I can rewrite this to be 2 over 3, and then the cube root of x. And now we're going to go ahead and plug in 0. F prime of 0 would equal to 2 over 3 times the cube root of 0. Now that is just equal to 0. So we get another scenario where we have an undefined value for the derivative. This means that f of x is not differentiable at x is equal to 0. So even though my function here was continuous, it's still undifferentiable, and we'll discuss that in a bit. Now we're going to look at the graph of g of x is equal to 3 over x plus 1. Based on this graph, is g of x continuous at x is equal to 1? So again, I'm going to go through my process here for continuity. So I'm going to find g of 1. And g of 1 is equal to right here, which is right in between, so about 1.5. I could also plug it into my function. 3 over 1 plus 1 is 3 over 2. So again, 1.5. Now I'm going to find my limit. The limit as x is approaching 1 of g of x is the same value because the limit from the left does equal the limit from the right. So therefore, my limit is also equal to 3 over 2. So here I would state that g of x is continuous at x is equal to 1 because g of 1 is equal to the limit as x is approaching 1 of g of x, which is equal to 3 over 2. Now we're going to see if we can find that derivative. So we're going to find g prime of 1. So first I'm going to need to find the derivative of g of x. Now when you look at this function, most of the time we want to automatically go ahead and use the quotient rule, which you absolutely can. You'll get the same answer. However, I like to kind of simplify this in the sense that if I don't have to use a quotient rule, I try not to because it is a lengthy process. So instead what I can do is I can rewrite this function as 3 times x plus 1 raised to the negative 1. So what I did was I moved the denominator up and made it into a factor, and I changed the exponent to a negative exponent since it was in the denominator. Now here the 3 is just a constant, or a coefficient rather, so I would just apply the chain rule to this function. So g prime of x would equal to negative 3, because I'm multiplying the negative 1 with the 3, x plus 1, subtract 1, so raised to the negative 2, times the derivative of x plus 1, which is just 1. So g prime of x is equal to negative 3 over x plus 1 squared. And now I'm ready to plug in 1. So g prime of 1 is going to equal to negative 3 over 1 plus 1, so 2 squared, which is equal to negative 3 over 4. So here I do get that my function is differentiable at x is equal to 1 because I actually got a numeric answer. Now we can also verify these results with the graphing calculator. Let's have a look at that first function. So I'm going to graph this x raised to the 2/3 plus 2. And now I'm going to go ahead and find that derivative. So second calc, I'm going to go down to dy dx, and I'm going to click on 0. And we get here that it equals to 0. Now we know just by doing the work here by hand that this is not true. So if you get something like this, you have to know that it is undifferentiable. And I will explain again in a moment why it's undifferentiable at that point. So the calculator won't know. I'll get into it in a bit. Okay, let's look at the second function, however. We have 3 divided by x plus 1. Now I'm going to graph it. I'll go to second calc for dy dx, and I'm going to click on x is equal to 1, and I get negative 0.75, which is negative 3/4. So everything looks good. Now, why did this end up giving me 0? Now, here's the thing. The calculator can only do so much for us. There's a lot of things that we need to keep in mind. A function is differentiable if 2 things are true. 1, that the function must be continuous, as we noticed that if the function was not continuous, we did in the first example, we did not get a differentiable function. And that it has no cusp. A cusp is a point. So see here how it comes to a sharp point. This is considered to be a cusp, and that's why it is undifferentiable. However, the calculator does not recognize that it is a cusp. Sorry, I don't know why I pulled the calculator back up. It doesn't recognize that it's a cusp. So it calculated the derivative as if it wasn't a cusp. So we have to know, okay, I see a cusp, it is not differentiable at that point. And then the second condition for differentiability is that the limit as x is approaching whatever value it is that we're given from the left and from the right of f prime of x must equal to 0, must equal to each other. So if I look here at these graphs, which of these would we say is differentiable at x is equal to 0? For this first graph, I see that I have a vertical asymptote at x is equal to 0, meaning that my function is not continuous here. And if it's not continuous at that point in time, then automatically it is not differentiable. Here we have a parabola, and at x is equal to 0, it is not only continuous, but smooth. There is no curves. So therefore, this one would be differentiable. And then here we have the absolute value function, and even though my function is continuous, I have a cusp. So therefore, my function would not be differentiable at x is equal to 0. Now, here's where we're going to start getting into a more analytical perspective. We're looking here at a piecewise function. We don't have the graph, but we want to determine if the function is both continuous and differentiable at x is equal to 3. Now, in the past, when we were doing our unit on limits, we did discuss continuity, and we did do questions like this and just showing if the function was continuous or not. However, now we're adding an additional element to determine if the function is also differentiable at that point in time. So let's work this one out. We have g of x is equal to the square root of x plus 1 for when x is between 0 and 3, and we have that g of x is equal to 5 minus x for when x is between 3 and 5. So first we're going to determine if the function is continuous. So we have to go through that 3-part definition. So first I'm going to go ahead and find g of 3, since I'm trying to find if it's continuous at x is equal to 3. So I look here at my piecewise function, and x is equal to 3 is defined here because of the inequality. And so I'm going to plug in 3 into this part of my piecewise function. So we get the square root of 3 plus 1, which is equal to the square root of 4, which is equal to 2. So that's my defined value. Now my defined value is also the limit value from the left. So in order to determine the limit of g of x as x is approaching 3, I need to now find the limit as x is approaching 3 from the right of g of x. So I'm going to plug it into this bottom equation here, and I get 5 minus 3, which also equals to 2. And since this is the right limit and this is also the left limit, then we can safely say that the limit as x is approaching 3 of g of x is also equal to 2. So what does this mean? Since they are equal to each other, this means that g of x is continuous at x is equal to 3. And we would say because g of 3 is equal to the limit as x is approaching 3 of g of x, which is equal to 2. Now we're going to see if g of x is differentiable at x is equal to 3. And in order to determine that, that means that the limit as x is approaching 3 from the left of g prime of x must equal the limit as x is approaching 3 from the right of g prime of x. So I'm going to go ahead and find the derivative of the left side and the right side and see if they equal to each other. So let's start with the limit as x is approaching 3 from the left of g prime of x. Now when I find g prime of x for the left side, this is equal to x plus 1 raised to the 1/2. So the derivative would be 1/2 x plus 1 raised to the negative 1/2, which is equal to 1 over 2 square root of x plus 1. And now I can go ahead and plug in the 3. And I get 1 over 2 times the square root of 3 plus 1, which is 4, which gives me 1 over 2 times 2, so 4. This means that the limit as x is approaching 3 from the left of g prime of x is equal to 1 over 4. So now we're going to go ahead and find the limit as x is approaching 3 from the right of g prime of x. Now g prime of x from the right, if I find the derivative, 5 minus x, I get negative 1. And therefore, because the limit from the left does not equal the limit from the right, we would say g of x is not differentiable at x is equal to 1 because the limit as x is approaching 1 from the left of g prime of x does not equal the limit as x is approaching 1 from the right of g prime of x. Now let's look at some examples where you're going to have to make a function both continuous and differentiable. And I tried to break this down as much as possible and give you some steps here to follow. So basically, you can read through this and follow your steps, but what this says is that in order to determine, or rather, in order to make the function continuous, we would have to do 3 things. 1, make the limit from the left equal to the limit from the right. So we're going to write our limit statements. Once we write our limit statements, we write the corresponding equations based on the piecewise functions. And once we write those corresponding equations, we go ahead and plug in the x value that was given. After you plug in the x value, you would be left with an equation with 2 variables since we're solving for k and m. Then, in order to make it differentiable, we would have to set the limit from the left of the derivative equal to the limit from the right of the derivative, and then do the same thing. Write the corresponding equation, and then plug in the x value, and we would end up with a secondary equation with the variables k and m again. So once you have those 2 equations, then you put them together and it creates a system. So let's go ahead and go through this process. So I'm just going to go and follow along with these steps here so you understand what I was explaining. So first we're going to determine if the function is defined at the indicated x value. When I look here, my x value here is 3, and I see that 3 is defined. So that part of continuity is taken care of. And since I don't know what k is, it's not like I can plug in 3 and get the defined value. So really what I need to do here is set up our limits. So we've done step 1, we've already verified it is defined. Now we're going to set the left side of the function equal to the right side. So that's our limits. So the limit as x is approaching 3 from the left of h of x has to equal the limit as x is approaching 3 from the right of h of x. And now I'm going to write those corresponding equations. So k square root of x plus 1 is equal to m times x plus 2. Now we're going to go ahead and plug in the x value. So that's what I was saying. Remember, limit, equation, now plug in the x. So k times the square root of 3 plus 1, so 4, is going to equal to m times 3, so 3m plus 2, which is essentially 2k is equal to 3m plus 2. This is one equation that I'm going to hold on to and we'll come back to. So now we're going to step 4. Find the derivative of the left and the right side and make them equal to each other. So what this means is that we're going to write the limit as x is approaching 3 from the left of h prime of x, and we're going to make it equal to the limit as x is approaching 3 from the right of h prime of x. Remember to always write these limit statements. So that's step 4. And now we're going to actually find the derivative of each one of these. Now remember that this k and m, they represent coefficients. They do not represent actual variables, even though right now they are variables. So when you find the derivative, you treat k like a coefficient. So the derivative of h prime of x, remember that part of the piecewise function is k times x plus 1 to the 1/2, is going to equal to half k times x plus 1 raised to the negative 1/2, and we're making it equal to the derivative of the left side, which would just be m. So now I can rewrite this to be k over 2 square root of x plus 1 is equal to m. And now for step 5, we're going to plug in the x value, and then we'll be left with our second equation. So the x value, remember, is 3, so it will be k over 2 times the square root of 3 plus 1, which is 4, is equal to m, which makes it k over 2 times 2, so 4, is equal to m. Now, this would be my other equation. So these two here create a system. So what I do is that I'm going to write them now together. So that's the last step. The two equations you found are now a system that you can solve using either substitution, forgot a T, or elimination. So that's what we're going to do now. We're going to make k, we have the two equations, 2k is equal to 3m plus 2, and we have the equation k over 4 is equal to m. Now you can choose to use substitution or elimination. As I said, in this particular case, I would use substitution because m is already solved for. So I can take k over 4 and plug it in for m. So therefore, we get 2k is equal to 3 times k over 4 plus 2. Now here's my own suggestion. I really hate working with fractions most of the time, so if you ever want to just eliminate a fraction, look at what the denominator is, and I'm going to take that denominator and I'm going to multiply it to the entire equation. So that way that fraction will cancel out. So my equation would now read 8k is equal to 3k plus 8. And now I solve for k. So here I would just subtract the 3k, and I get 5k is equal to 8, and so k is equal to 8 over 5. So once you have one variable, to solve for m, all you have to do is plug in k. So that's what I'm going to do now. I'm going to plug it in right here, since I have an equation already for m. So m is going to equal to k, which is 8 over 5 over 4. Which, remember, this is a fraction and we're dividing it by 4 over 1, so copy, change, flip. So m would equal to 8 over 5 times 1 over 4 the 8 and the 4 can be simplified to 2. So my m value is 2 over 5. So just to kind of summarize this process, we write our limit for continuity, we write the equation, we plug in x. We write the limit for the derivative, write the equations, plug in the x. Put the two equations together to create a system, and then you solve for your variables. Let's try one more. For what value of a and b will the function be both continuous and differentiable at x is equal to 1? So here we have f of x is equal to 3ax squared plus 2bx plus 1 for when x is less than or equal to 1. And then we have ax to the fourth minus 4bx squared minus 3x for when x is greater than 1. So let's start with continuity. So I'm going to start off with my limit as x is approaching 1 from the left of f of x is equal to the limit as x is approaching 1 from the right of f of x. Now I write the corresponding equations. So 3ax squared plus 2bx plus 1 is going to equal to ax to the fourth minus 4bx squared minus 3x. Now I plug in the x is equal to 1. So when I plug in x is 1, basically I just end up with whatever is left over. So 3a plus 2b plus 1, because when I plug in x, you just 3a times 1 essentially, etc., is equal to a minus 4b minus 3. Now, knowing the nature of these kinds of questions and that I'm going to have to set up a system, what I would do in this particular case is I would move all of my variables to the left and my constants to the right, so that way when I get my second equation, it's easier to line up together. So I would subtract this a, add the 4b, and then I would subtract this 1 so that my constant is on the other side. So now I end up with the equation 2a plus 6b is equal to negative 4. And remember, I'm going to go ahead and just put a little note by this one because I'm going to have to come back to it. Let's move on now to making it differentiable. So again, we start off with our limit. The limit as x is approaching 1 from the left of f prime of x should equal to the limit as x is approaching 1 from the right of f prime of x. Now remember, a and b are considered coefficients. So when we find the derivative of this, it is not a product. We just treat a as if it's part of the number. So when I find the derivative of the left side, that is just the power rule. So we would get 6ax plus 2b, that's for the left, is going to equal to 4ax cubed minus 8bx minus 3. And now we plug in x is equal to 1, and that would give us 6a plus 2b is equal to 4a minus 8b minus 3. And again, I'm going to do what I did last time, which is I'm going to move my a's and b's over to the left side and any constants over to the right. In this case, I just have to subtract this 4a and add the 8b. And that's going to give me the equation 2a plus 10b is equal to negative 3. So now that I have my two equations, I can put them together so that I can solve for a and b. So I'm going to just line them up. 2a plus 6b is equal to negative 4, and 2a plus 10b is equal to negative 3. And again, you can solve this using substitution or elimination. In this particular case, I would prefer to use elimination only because I see here that I have 2a and 2a. So if I multiply one of these equations by negative 1, the a's would cancel. So I'm going to go ahead and multiply negative 1 to this bottom equation. I'm going to keep this equation, so I'm just going to rewrite it. So 2a plus 6b is equal to negative 4. And the bottom equation becomes negative 2a minus 10b is equal to 3. My a's here cancel, and I'm left with negative 4b is equal to negative 1. And when I divide by negative 4, I get that b is equal to 1 over 4. Now I'm going to have to solve for a. So you can choose to plug it into any one of your original equations. I'm just going to plug it into that first one there. So 2a plus 6 times b, which is 1 over 4, is equal to negative 4. Now 6 times 1 over 4 is 6 over 4, which can be simplified to be 3 over 2, which is equal to negative 4. And again, I don't really want to work with this fraction. It's not like it's that hard, but I just don't feel like it. So what I'm going to do is I'm going to multiply this entire equation by 2 to cancel out the denominator. And when I do that, that's going to give me 4a plus 3 is equal to negative 8. Here I would subtract the 3. I get 4a is equal to negative 11, and then divide the 4. So a is equal to negative 11 over 4. And that's differentiability and continuity.